Hello, this is Proximity Math. Today we're gonna do the 2005 Aime Ii number 13. Let p of x be a polynomial with integer coefficients that satisfies p of 17 equals 10 and p of 24 equals 17. Okay, given that p of n equals n plus 3, this equation has two distinct integer solutions. Find their product. So there's two distinct integers such that p of n happens to be n plus 3. Alright, so what do these two facts tell us? First of all, notice 10 is 7 less than 17, and 17 is 7 less than 24. Maybe that can tell us something. Like, if we let f of, okay, if we let another polynomial q of n be equal to, so I'm gonna let it be x, q of x, okay, equals p of x minus 7 less than x. So what this does is it makes 17 and 24 both roots, because 17 is equal to the p of 17 is equal to 7 less than 17, and the same goes for 24, which means q of 17, which is also q of 24, equals 0. And what does that also mean? It means q of x is equal to some polynomial. I'm gonna let it be small q of x times x minus 17 times x minus 24. And now to get p of x, we can add back x minus 7. Alright, we have this equation for p of x. We can add back it. Okay. Next, from this, if it has two integer solutions, that just means p of n minus 3 less than n, because, sorry, 3 more than n plus 3. If we let this be r of n, pqr of n, then r of n will have, I'm gonna let it be small r again, small r of n times s2 roots x minus n 1 x minus n2. Alright. So first of all, let's look at this closer. Okay. So what if we plug in r of 17 and r of 24? And we can use this formula here. So we get negative 10, and then we're subtracting 3 more than 24. We also get negative 10. So we have the fact that r of 17 equals r of 24 equals negative 10. But this fact right here, it shows that these two are symmetric from the line of symmetry of the roots. These two are symmetric from the average of the roots if they have the same value. Because if you ignore r of n for now, let's just say it didn't exist, then maybe it would be a good idea to guess it's a quadratic. Yeah, a quadratic can satisfy everything. So that means, and I'm gonna, so yeah, never mind. Okay, n1 plus n2 over 2 equals 41 halves, which is the average of these two. So that's, we can get the sum straight from here. All right. Now, what else do we also get? Let me see. Okay. So, okay, what about Q of x? Wait a second. Oh, never mind, never mind. Okay. So from here, if we know that these two are equal, right? What does that give us? Well, if we can cancel out the a afterward, but if we take a times, if we plug it into R of 17, we can 17 minus n1 times 17 minus n2. That's equal to a times, which is the leading coefficient, by the way. Make sure you don't forget about that. Okay, it's equal to R of 24. It's 24 minus n1, 4 minus n2. Or cancel out a. You get 289. Or actually, I'm gonna leave that for a reason. Okay, 17 squared minus 17 times n1 plus n2, which we know is 41 from over here, plus their product. Okay, I'm gonna let their product be p because it cancels out if you actually look. Product is equal to 24 squared minus 41, 24 times 41 plus p. Okay, I'm gonna take away p from both sides. And actually, if this is true, that means R of n and all these polynomials are quadratics. Otherwise, my logic here is wrong. Okay, so we have 17 times 41. That's negative 408 on the left side, and we get negative 408 on the right side. That means P is a quadratic because it is indeed symmetric from the roots. Like, what I did is use the fact that, sorry, R of 17 and R of 24 have the same value, and I used the average of these to find the sum of the roots. That only works if it's a quadratic. I mean, it generally works. So now we have confirmed it by substituting into R that the sum is 41. Alright. So now that we know it's a quadratic, I can clear this off and replace it with a. Alright, so what else do we do now? Well, if I substitute directly into P, for example, okay, I have P of 17 is equal to, so 10 is equal to 8 times x minus 17, which is already there, and same for 24. This term is 0 for both 17 and 24, but not this term. Okay, never mind. That doesn't give us any new information. So what do we look at next? Let's see. Okay. Okay. What about? Okay, this has two integer solutions. R of n. Do you look at R of n? Alright, we have this information. I'm trying to find a way to use it again. We have n1 plus n2 equals 41. Okay. So the roots of R are n1 and n2. and I'm gonna expand it in quadratic form. Minus 41x plus their product is equal to, this is r of x, r of n, sorry, or whatever, okay, r of x, which is p of n, or p of x minus n plus 3. This is equal to p of n minus n plus 3 p of x. So how do we simplify this? Okay, first of all, we can take this and turn it into a times x squared minus 41 41x plus their product 17 to 24, which turns into 408 if you do the math. Okay. 408 plus x minus 7. And be careful, this part's being multiplied by 8. Okay, minus n plus 3. So subtracting x plus 3, we get minus 10. Right. So minus 10. Alright. This is equal to a times all of this. Okay. It's equal to a times x squared minus 41x and so on. Okay. Alright, so wait a second. These are separate A's probably. Are they? We have A and then we have a B here. Alright. But the x squared must be have the same coefficient. X squared must have the same coefficient. Alright. So we have these two equations. I'm gonna divide everything by A. What I did was equate r of x to p of x minus n plus 3. Alright. And I'm gonna cancel all the everything with x and get this. Alright. Now we're literally one step away from finding our product. Alright. So we have our product. We have n1 plus n2 equals 41, right? And then our product is equal to n1 times n2. So this is equal to this is equal to n1 plus n2. And then p is equal to n1 times n2. We need to find the integer solutions to this. If we try taking the middle, like maximizing the product, you get 20 times 21. 20 times 21 equals 420. Can we get from 408 to 420? And we need integer coefficients. Alright. We have a polynomial with integer coefficients. Alright, so we need to find another pair that satisfies this, because what are the possible values of this? Okay, we can have 10, or if a is equal to 10, we have 1. This is equal to 1, 2, 5, or 10, depending on a. and also it can be either the minus or the plus value. Okay, so from this we can get 410, for example. We can get 418, but we can't get to 420, which means we can't use this. Okay, next we can use 19. We can increase them out. We can decrease one and increase the other one to get the next highest product. This is equal to 418, which is indeed achievable by making a -1. A can be -1. Let's go to 418. So we have n1. It doesn't matter what the order is. Our solution would be n1 equals 19 and n2 equals 22. Alright, so the final answer is just 418. And what this used was, this used quadratics, transformation of quadratics by the roots. This is called quadratic interpolation. And basically you can equate things and use the advantage of the roots, take advantage of the roots, and then you solved for the only possible pair. Alright, thanks for watching, and I hope this helped you.